This problem that we're looking at is very similar to one that we did in the previous chapter, where we looked at the work that a spring did on a box, and we used it to find the kinetic energy that the box gave. We used the work energy theorem, where the net work equals the change in kinetic energy. This method is a similar method. It comes from the same stuff, but it's using conservation of energy instead. To do this problem, first we need to know that the potential energy of a spring is 1/2 kx squared. In this equation, k is the spring constant, or the force constant, that describes how easy or difficult it is to stretch the spring, or the stiffness of the spring. X is the distance that the spring is either stretched or compressed from its unstretched or equilibrium position. In this problem, initially the spring is compressed by a distance of 20 centimeters. So that's a distance of 0.2 meters. So we can first calculate the initial potential energy that's stored in the spring. That initial potential energy is going to be 1/2 times the spring constant, 20 newtons per meter, times the distance that the spring is compressed, 0.2 meters squared. And this gives 0.4 joules of potential energy stored in the spring. That potential energy comes from the work that you would do compressing the spring by that distance. The work that you did does not turn into kinetic energy of the box. It ended up getting stored in the spring to be released later on. Because the box is initially not moving, the kinetic energy at the beginning is 0 joules. Again, kinetic energy is 1/2 the mass times the speed squared. And so to solve this, we're going to use the principle of conservation of energy. And this principle says that if there are no non-conservative forces doing work on the object, then the total mechanical energy stays constant. The total mechanical energy is the potential energy plus the kinetic energy. So the potential energy plus the kinetic energy at one point, let's say the initial point, equals the potential energy plus the kinetic energy at some other final point. Again, this refers to any 2 points in the motion of the object. If you look at the total mechanical energy at any point along the way, it's going to equal the same value if there are no non-conservative forces doing work. So if we put in our values, we have that the initial potential energy was 0.4 joules. The initial kinetic energy was 0 joules. At the end, the spring is not compressed at all, so the potential energy stored in the spring now is 0. And if we wanted to find the final kinetic energy, we would just leave k final in our equation. Because this question asks us for what the final launch speed is, we'll replace the final kinetic energy with 1/2 times the mass, 0.1 kilograms, times the speed squared. And if you solve this for the speed, you get that the speed of the block is 2.828 meters per second. Again, this is a very simple example where there's only one type of potential energy. The block was not moving up or down at all, so we did not have to worry about gravitational potential energy. All we had to worry about was the potential energy stored in the spring. In the problem that we looked at in class, we had something that was a little bit more complicated. We had something where there was something moving vertically, and it was also stretching a spring. And so we looked at the potential energy at the top. The potential energy at the top was the gravitational potential energy at the top plus the spring potential energy at the top. We know what the height above the water was, so we found what the gravitational potential energy was. The spring, or the bungee cord, was not stretched at all, so there was no spring potential energy at the beginning. The person also started from rest, so there was no kinetic energy at the top. And then they jumped down, and when they reached the lowest point in their motion, they also stopped. So at the end, the kinetic energy was also 0. But at the end, we had a mix of gravitational potential energy, because the person was still some height above the water, and we also had some spring potential energy, based on how far the person stretched. That was this distance d. If we look at that, that distance was the full length from the top to the water, 45 meters, minus the unstretched length of the bungee cord, 25 meters, minus the height above the water, h. So we use that to get that equation, 1/2 times the spring constant, 160, times the distance that it was stretched, d, which was 20 minus h. So we went through and we solved that, and we found the height above the water that the person reached. Again, this is a slightly more complicated problem because there are two types of potential energy that you have to take into account. But you don't approach this problem any differently. You just make sure that you include all of the types of potential energy that you have. Again, we did this problem in class. We had the box starting on the ramp, and it went around the track, and we were looking at the top of the loop. And first we found the minimum speed that the box must have to not lose contact. So this box was moving in a circle. So at the top of the loop, the net force is the force of gravity plus the force of the track. They're both pointing in towards the center of the circle, so they're both positive. And net force is also mass times acceleration. Again, here the acceleration is the speed squared divided by the radius. If we're looking for the minimum velocity that it can have without leaving the track, that's when the force on the track is 0. The minimum, the smallest that the net force could be, is when the force of the track is 0, and all we have is the force of gravity. And what we're looking for is when that force of gravity is still causing it to move in a circle. If it moves slower than our minimum speed, then it actually falls out of the circle. But we're looking at it still moving in a circle, so the acceleration is still the speed squared divided by the radius. And so we went through and we solved this. We get that the minimum speed at the top of the loop was the square root of the radius of the circle times g, 9.8 meters per second squared. And so that gave us a speed of 4.427 meters per second. To find the minimum height that it must be released from to go around the loop and not lose contact, we use the idea of conservation of energy. So at the beginning, the box was not moving at all, so there was no kinetic energy at the beginning. And it was some distance h above the ground, so it had a certain amount of potential energy. The mass, 1 kilogram, times g, 9.8, times the height, h. At the top of the track, the height is not 0. The height was 4 meters above where we called the height 0, which was at the bottom of the track. So there was potential energy at the top. It was the mass, 1 kilogram, times 9.8 times 4 meters. And there's a certain amount of kinetic energy at the top. We were looking for what we were looking to make sure that this velocity was going to be at least 4.427 meters per second at the top. So we find what the kinetic energy is at that point. We plug that into this equation, and that gives us our total mechanical energy at the top of the loop. If we know the total mechanical energy at the top of the loop, we know what the total mechanical energy is anywhere along the path, and so that allows us to find the height. The minimum height that it must be released from is 5 meters. If it's released from a height that's bigger than that, it's going to give us a speed that's bigger than 4.427 meters per second, which means that it will be on the track and the track will be pushing down. We are going to see that in our next slide. So this problem we did not look at in class. So we have this box starting from a height of 8 meters. So it's bigger than the 5 meters that we had before. And again, it's still sliding around the same loop of radius 2 meters. And so now we're going to find the speed at the top of the loop. So we can first find the potential energy when it's starting. So that potential energy is going to be 1 kilogram times 9.8 meters per second squared times the height of 8 meters. And so if we calculate that potential energy, it's 78.4 joules. This box is starting from rest, so the initial kinetic energy is 0. It doesn't need to be starting from rest. if it was moving at 3 meters per second at the beginning, we would just include what the kinetic energy of something moving 3 meters per second would be. It would be a half times 1 times 3 squared. But in this case, it's starting from rest, so there's no kinetic energy at the beginning. When it reaches the top of the loop, again, it has some potential energy. It has that potential energy that we found before. So the potential energy at this location here is going to be the mass of 1 kilogram times 9.8 times a height of 4 meters. And that is 39.2 joules. So we'll call this the final location. The kinetic energy at the final location is what we're looking for, and that's going to be 1/2 times the mass times the unknown speed squared. And so if we look at this, if we put these things together in part C, again, we have no non-conservative forces that are doing work on this object, so the total mechanical energy stays constant, or is conserved. So we look at the initial potential energy and the initial kinetic energy, and we set that equal to the final potential energy plus the final kinetic energy. Again, we use initial and final to describe these, but really they're any 2 points along the motion. It doesn't have to be the final location does not need to be where it ends. It's just some point along the motion. So we plug in the initial potential energy of 78.4 joules plus the initial kinetic energy of 0 joules and set that equal to the final potential energy, which is 39.2 joules. If you notice, this loop is half as tall as the starting height, so it has half the potential energy. It's lost half of its potential energy. Half of its energy has been converted into kinetic energy. So this final kinetic energy is going to be 1/2 times 1 times the speed squared. So if we subtract 39.2 over to the other side, we have 39.2 equals 0.5 v squared. And if we solve that for the speed, we get a speed of 8.854 meters per second. Again, this is bigger than the minimum speed that we had before of 4.427 meters per second because it's starting at a height that's higher than the minimum height that we had before. So now, since it's moving faster than the minimum speed, that means that the track needs to push down on it some to keep it moving in a circle. But looking at the net force at the top of the circle is still the force of the track plus the force of gravity. Again, both of those are in towards the center of the circle, and so the convention is towards the center of the circle is the positive direction, away from the center of the circle is the negative direction. So if we were looking at something at the bottom of the circle, the track would be pushing up in what we would call the positive direction, but the force of gravity would be in the negative direction. It would be away from the center of the circle. But again, this is the same location that we were looking at before, where we're looking at the top of the track. And we also have that the net force equals the mass times the acceleration. But again, the acceleration is the speed squared divided by the radius. And so now we can substitute in some of the values that we know. So we set those two net force equations equal to each other, just like we've done in all of our force problems that we've looked at. We write the net force equals the individual forces added together, and the net force equals mass times acceleration. So in a lot of ways, this is similar to the elevator that moves up and down, and you need to find what the normal force, what the force of the elevator floor on the person was, or a block that's being pulled up or down by a rope, trying to figure out what the tension in the rope is based on its acceleration. This isn't something that's moving in a straight line, but it's the same idea. So we're looking for the force of the track plus the force of gravity, which is 1 kilogram times 9.8 meters per second squared. And we set that equal to the mass of 1 kilogram times the speed, 8.854 0.854 squared divided by the radius of the circle, which is 2 meters. And so if we do that, we have that the force of the track equals 9.8, force of the track plus 9.8 equals 39.2 newtons. And so if we subtract 9.8 from both sides, we get that the force of the track must be equal to 29.4 newtons. Again, if you know what the radius of the circle is and you know how fast it's moving, you can figure out what the force of the track is at that point, based on the fact that there is a specific acceleration that's in towards the center of the circle. After we looked at this, we talked about what to do if there were non-conservative forces acting. So if there are non-conservative forces that are doing work on the object, those forces change the mechanical energy. You have the initial mechanical energy, the initial potential energy plus the initial kinetic energy, but then the final mechanical energy is going to be a different value. You either have a non-conservative force that does positive work, which increases the mechanical energy, so your final mechanical energy is going to be bigger than your initial mechanical energy, or you're going to have a non-conservative force that takes energy away or does negative work on the object. In that case, your final mechanical energy will be less than your initial mechanical energy. Again, that's all built into this equation. So if the non-conservative force adds energy to it, the work is going to be positive. And so you're going to add a positive number into this equation, which will make your final energy bigger. If you have something like friction acting against the motion, friction doesn't always act against the motion. On your AP take-home test, you saw something where the force of friction did positive work on one of the blocks, on the bottom block, and pulled it forward. But if you have friction acting against the motion, like it was on the top block in that problem, that force of friction is going to do negative work. And in that case, you're going to add a negative number in here, which makes your final mechanical energy less than your initial mechanical energy. You need to include the positive or negative signs of the work in this equation. And we looked at a problem where this was true. We had this box that was sliding along at 4 meters per second, and it hit the spring and compressed the spring, but we also had friction acting. And so we looked at the initial potential energy. There was none stored in the spring. And we looked at the initial kinetic energy, which was 1/2 times 2 kilograms times 4 meters per second squared, which is 16 joules. And we looked at the work done by the force of friction. The work done by friction was negative because the force of friction opposed the motion. And it was 15 newtons times the distance that it slid, which is what we're looking for. And at the end, the object stops, so the final kinetic energy is 0. And the final potential energy is 1/2 times the spring constant of 10,000 newtons per meter times the distance d squared. And so we got this quadratic, and I left it to you to solve. I have here the answer. If you use your CAS and use the solve feature, you get that the distance, we want the positive answer. So the distance that it compresses is 0.055 meters, or about 5.5 centimeters. Again, this is a very strong spring. 10,000 newtons per meter would be about the strength of a garage door spring. So it's not going to compress very far, even though this box was moving 4 meters per second, or about 8 miles an hour. The final problem that we're going to look at in this set is almost identical to the problem that we started with. We have the same block with a mass of 0.1 kilograms, with the same force constant, or spring constant, of 20 newtons per meter, and it's compressed the same 20 centimeters, or 0.2 meters. The difference is we have friction. We know that the coefficient of friction is 0.1. So the first thing that we need to do is we need to calculate what the weight of this block is. The weight of the block is going to be 0.1 kilograms times 9.8. So this weight is 0.98 newtons. And that means that the normal force is also going to be 0.98 newtons. And the force of kinetic friction equals the coefficient of kinetic friction times the normal force. So if I plug in those two values, the coefficient of kinetic friction is 0.1 times the normal force of 0.98. We get that the force of kinetic friction is 0.098 newtons. That force of friction acts against the motion the entire 0.2 meters before the block leaves the spring. So again, we're going to use our more general conservation of energy equation. It's the conservation of energy equation that also includes the non-conservative work. So we look at the initial potential energy plus the initial kinetic energy plus the work done by the non-conservative force of friction. And we set that equal to the final potential energy plus the final kinetic energy. Technically, when we have no non-conservative forces acting, or at least no non-conservative forces doing work, we are using this equation also, but the work done by the non-conservative force is 0, so we leave it out of the equation. If you don't like using one equation for some things and one equation for other things, you can always use this equation. It's just there will be a lot of cases where there will be no non-conservative forces doing work, and so that term will be 0. So if we plug in our values, we have the same initial potential energy that we had before. That initial potential energy is going to be our 1/2 times 20 newtons per meter times 0.2 meters squared, which, just like it gave us before, was 0.4 joules. And initially it's not moving, so the initial kinetic energy is 0. So if we plug in those values, we have 0.4 joules plus the initial kinetic energy of the object, which is 0, plus now we need the work done by friction. And so let me calculate that over underneath the friction. So the work done by the non-conservative force of friction is going to be the force of friction, which is 0.098 newtons, times the distance that it slides of 0.2 meters. And because the force of friction is acting to the left and the motion of this block is to the right, if the force and the motion are in opposite directions, the work done by that force is negative. Again, that negative sign has nothing to do with a direction for work. Work is a scalar. That has to do with the fact that that force is taking energy away from the object. A positive work means adding energy to an object. A negative work means taking energy away from an object. And so if we calculate that, we get that the work done by the non-conservative force of friction is negative 0.0196 joules. If you would prefer to write the work done by friction instead of WNC, that's fine. The work done by friction is the work done by the non-conservative forces. So there's only one non-conservative force in this problem. So we include that work, negative 0.0196 joules. It is extremely important that we include that negative sign because it's going to take mechanical energy away. And then, just like we had in the other problem, the spring is not compressed at the end, so there's no potential energy stored in it. And we're looking for the speed, so I'm going to replace the kinetic energy with its equivalent, 1/2 0.1 kilograms times the speed squared. And so if I take 0.4 joules and I subtract the 0.0196 joules to take away the work, to take away the energy that friction got rid of, we have 0.3804 joules of energy is what we're left with. And that energy is all kinetic energy. So it's 0.1 kilograms times the speed squared. So if we solve for that speed, we get a speed of 2.758 meters per second. And if we compared that with our answer before, we got 2.828 meters per second. So without friction, we had 2.828 meters per second. And again, that's what we would expect. We would expect that if we have friction, it's going to leave the spring at a slower speed. And that's what we have. It left at about 1/10 of a meter per second slower. Again, we're going to do these types of problems more and more. Please give me feedback. Let me know if these worked out examples, storing them as movies, if it is helpful. Hopefully it is, and hopefully we'll be able to do a lot more with them.